Andy. He's going to talk about a transfer learning view on learning representations.
Okay.
Yeah, it's Archambeau. It's not that difficult. Okay, so first of all, I would like to thank the organizers for letting me speak about this topic. Essentially, those are two topics: learning representations and hyperparameter. Well, optimizations are two topics that I have been very passionate about for the last recently, and so it's kind of combining those two topics, and I'm really glad I can speak about those today here at DALI. So first one word on my co-authors. So this is joint work with Rodolphe Genaton and Matthias Seeger. You might have talked to Matthias, for example, yesterday in the poster. Some of the things that he presented yesterday is related to this work as well. But so both Rodolphe and Matthias are colleagues in Berlin. And Valerio was an intern with us, so he contributed to that work. He's a PhD, he's a finishing PhD student at the University of Warwick. Okay, so just to step back, so the general context I'm interested in those things is that now today we've seen like lots of applications, like lots of application of machine learning and especially deep learning, like gaining traction in like a very broad range of problems, going from self-driving cars to like voice assistants, traditionally like recommendations, search, and then now people are talking about also self-flying cars or walkout technology. So anyway, so all those innovations I think have accelerated recently, have been to a large extent driven by deep learning, but in the end, like deep learning can be applied to also less maybe high profile applications, and machine learning in general has like really a transformational like impact in businesses and probably on our lives through those products that are coming out today. So but the thing is that when you look at deep learning and you want to apply it in practice, it's still quite tricky. It can be painful, and it's tricky because it's like you need to have some expertise to know how do you set, for example, hyperparameters. So that's and if you want like more applications to be driven by those machine learning models or deep learning technology, well, you want people that are less expert being able to use that in practice. And so you want probably one of the things I'm interested in is like how can we automate that process, how we can automate machine learning. And here like hyperparameter optimization is one ingredient. And I think like learning representation is another ingredient that helps like boosting hyperparameter optimization in a wider range of problems. So just to set the general setting is like if you think about deep learning, well, if you want to have optimal performance, well, you have to look at all the different like parameters, which can be continuous, can be discrete, and it rapidly increases the number of things you have to tune. Now, if you would like to have like optimal performance, if you look at a convolution neural network, you have to look at the number of Hindle layers, you have to look at the activation functions, what type of regularization you're using, and then you also have all the parameters of your training, your optimization algorithms. So rapidly, this is exploding, and it can be like very time consuming to do that very carefully. So one very like straightforward approach to tackle that problem is either to have like a regular grid of configuration of hyperparameters and evaluate them all, maybe in parallel, or more interestingly, you can for example consider like a random grid. And in both cases, this is very pragmatic, but it's also very wasteful of essentially resources, because you can potentially evaluate them in parallel, but you will have to evaluate all those configurations and wait until they're finished before you know which one is the best one. You might want to add some additional ones or refine some parts of the space, but essentially it's very time consuming, very costly, and when you have to collect the results, analyze them, it's also prone to error, and if you would like to revisit them, it's again like a bit of a nightmare. The other, I think, more important aspect in the context of this workshop is that it's memoryless. So essentially, whenever you like have a new task, you have to start from scratch. And if you take one of those approaches, you cannot like leverage some prior information or some information that you accumulated over time to make that more efficient and maybe look at parts of space that are more interesting. So the question is, can we do better? Can we, for example, include like leverage information that we've collected in the past on related tasks to speed up this hyperparameter optimization problem? And so what I'm interested in here is a transfer learning at the level of hyperparameters. And so if you assume you have like a first like hyperparameter optimization job, so here on the left you have like, this is like the dots, the small dots here are configurations, a random grid of parameters you would like to evaluate or have evaluated so far. And then you have like essentially like the function you like to optimize, so you have like the minimum is in the center in red. So you can assume you have like under this like curved, probably a quadratic or something. And then you have another hyperparameter optimization job that a second one on some related problem. So essentially the function you'd like to optimize or minimize is either a similar shape, but maybe there's a little bit of a shift and a bit of a deformation. And again, you can like evaluate a random grid of those hyperparameters. And so you can continue that and have eventually like k of those hyperparameter jobs. And so if you would like to tackle now the kth one, well, you can again generate this random grid, or you can say, well, given what I've learned so far, and I generate this random grid, well, maybe there are some of them that I can just discard. Some of them are not really useful to evaluate or less promising to evaluate a priori. And so I've indicated like some green ones that potentially of what I've learned so far, those are the candidates I would like to evaluate in the first place before some other ones. And this is essentially what I would like to discuss today and see how one potential approach to do that, how you can learn a representation so that you can do this transfer learning and find those more promising candidates to evaluate instead of being agnostic about the problem that you're trying to tackle. So the general context is democratizing ML, like automating machine learning. And I typically think about it as like there are two ways of, two fundamental aspects I would like to, that you have to automate. The first is like, well, if you would like, for example, engineers to use your models, well, you want to abstract away training algorithms. And so if you would like to abstract away training algorithms, then you need to automate the process of hyperparameter optimization. So this can be done, for example, through Bayesian optimization. I will talk about it a bit more afterwards. And the second aspect is abstracting away representation. I think this is something in the topic of the workshop. I think this is very important. And there are multiple reasons for doing that, but one reason is to be able to leverage like information you've accumulated in the past and do transfer learning. So a quick discussion about like Bayesian optimization or black box global optimization. So what we're trying to do here is that we have some function f, which is non-convex, and the dimensionality of the input space is like moderate. It's about like, let's say like around 20 or so. And the key point is that you would like to optimize this function f, like minimize it, but well, you have a couple of additional complications. That first, your function is expensive to evaluate, so every evaluation at some x configuration, like configuration of hyperparameters in this case, can take a lot of time, or is maybe very expensive in terms of budget. The second thing is that you have no analytical form of per se of the function, so you cannot compute gradients. And then the third thing is you might have also noisy evaluation, so you might not have the exact evaluation of your function. So getting back to the tuning of deep neural nets, well, what does that mean? F can be, for example, your validation loss, and as a function of the hyperparameters. And so in this case, when you have like very complex models, well, training one of the models can take up to 2 weeks. So that's what I mean by something which is very costly. So you cannot afford to do many of those evaluations, which would probably be like a different setting. So you can typically don't afford to do a lot of evaluations, and so whatever you can use from the past that you can leverage, that you accumulated to speed up that process or make this search, like the evaluations, more interesting, is something that you would gain for performance and for speed of finding the best model. So one popular approach to apply, or like a relatively successful approach for doing this global black box optimization, solving those black box optimization problems is Bayesian optimization. And at a high level, it's relatively simple. So we have this function f we'd like to minimize. And you can think about the canonical algorithm for approaching the problem is by first assume you have like a surrogate model m, which is much cheaper to evaluate than your function f. And I will talk about which models can be used here. So you have a surrogate model m, and then you have a set of candidates. Can be this random grid, can be something else. But essentially you have a set of candidates you like to evaluate. And then while you still have budget, you're going to select one very promising candidate among those candidates to evaluate. Score them according to your surrogate model, and essentially you're going to look at the exploration-exploitation trade-off to find what are the most promising candidates among your the most promising candidate to evaluate among all your candidates. You're going to evaluate that candidate, so you get a new observation y new here. This is time-consuming, but that helps you now updating your set of candidates you already evaluated, and helps you, and you can then update your model, your surrogate model, and repeat this until you run out of budget. So what is a good way of, what's a very effective way of building such surrogate models? Well, you can do that with Gaussian processes, and Gaussian processes here are working very well because they're in a setup where you have relatively few observations. And so you have a probabilistic model which has a Gaussian likelihood, some residual noise sigma square, and you assume you have a Gaussian process prior over your function space, so over your target function. You try to learn that based on the different evaluations. So assume you have like one evaluation yi at your observation or configuration xi, you can start like building a model, and so gradually you have you have the mean function, which is essentially your surrogate model, and then you have some uncertainty around this mean function that you can leverage to do some exploration-exploitation trade-off. So for every new, once you have given the observations, you can compute like a predictive mean and a predictive standard deviation or predictive variance, and you can query f repeatedly. So what does that mean in practice? Like very briefly. So if you have this here, you have like the function f in green and a couple of evaluations here. Well, and you have like the green or the yellow line is essentially your minimum so far. So you have sequences of, so the big crosses here are evaluations that you selected and evaluated. You can build this surrogate function here, which is the black line, and then in regions away from your observations, you have some uncertainty. And so the way to select a new candidate is to use a utility function, like in this case, this is the expected improvement, or acquisition function in this case, and that's going to score the whole range of your domain and tells you what's the most next promising candidate given the observation that you've seen so far. So in this case, we have like at the red line, this is the most interesting location given what you've observed so far, and so you can avoid that point and gradually move towards the optimum, the minimum of your target function. Okay, so what's wrong with using Gaussian, like a Gaussian process surrogates? Well, in some sense, in the general setting where you have like one Bayesian optimization, one hyperparameter optimization task that you tackle one at a time, I think is very powerful because you have like a model-based approach. You have a good way of estimating promising candidates, and typically in a regime where you have relatively few observations that you can afford to make. Now, if you'd like to go beyond that, you'd like to do hyperparameter transfer learning. Well, and if you take like a naive approach, you can, like say you have a number, you have k hyperparameter optimization jobs, well, rapidly you're going to get into trouble because you have too many observations. And if you can also take like more fancy GPs, but in all cases you will get into trouble because it will be much like more time consuming to evaluate next candidates and to accumulate that information, especially if you like to accumulate information over a very large number of jobs or maybe over a long historical data set. So the bottom line is that this is scaling on cubic in number of evaluations. And so instead of using Gaussian processes, what we'd like to do is like a very cheap, like a very pragmatic and an effective way of doing that, that could replace potentially Gaussian processes, in this case of transfer learning for hyperparameter optimization. So what we used in this work is adaptive Bayesian linear regression. And so ABLR, for short, is essentially a Gaussian linear model. So it's a very simple model where you have like a Gaussian likelihood and you have a Gaussian prior over your parameters W. So you have like, the interesting bit is that you have essentially your function phi of z here, which is a set of features, like a basis expansion. And the question, how do you have like an effective way, like a useful way of representing your data so that you can do, like, for example, transfer learning. So I will talk about it like in the next slide, but essentially you have like some basis expansion, some weights W, and so you can, if you have, because it's like a Gaussian linear model, you can integrate out, you can compute in analytical form the posterior distribution over W, and you can integrate out the weights. So you get like a nice predictive distribution, meaning that you have like an approximation of your surrogate model with some measure of uncertainty. Now this is a linear model, so this is way more effective than inference, for example, in a Gaussian process. So this is the case for a simple ABLR. So now, if you'd like to do transfer learning, we're going to extend that to the multitask setting. So essentially what we're going to assume is that for every new hyperparameter optimization job, you will have one Bayesian linear regression model that you have to learn for the new task. And so the key point is that you will have that, you will share some part of the information. And what you're going to share is the representation. And the representation is this feature expansion phi of z, which is phi, like z is being the parameters of your basis expansion. And these shared features are going to be shared across all your hyperparameter optimization tasks. So you can take a very naive approach or a very simple approach by having explicit feature set, like for example RBF kernels, or you can use like random kitchen sinks. But what we're going to do here is we're going to learn this representation to a fit for neural networks. So you will have like a number of Bayesian linear regression models on top with a shared neural network underneath. The other aspect is that you're going to look at, we have this probabilistic model, so we also have like a multitask objective, which is going to be, since we can compute the log marginal probability for every task, we can just aggregate over all the tasks and have a sum over the log marginal probability of the observations. So a very nice way of combining tasks and potentially adding tasks to your set. So at a high level, what we have is this. We have like, for every new hyperparameter optimization job, we have like a Bayesian linear regression model here. We have a shared underlying neural network. And so X are the inputs, Z are the parameters of your neural networks, essentially your weights. And then at the Bayesian linear regression models, we have essentially two parameters, alpha t and beta t, which are the noise parameters, the scaling parameters. And this is because we're integrating out the W's so that you get like good estimates of the uncertainty for every new task. They're all coupled to like a shared objective. So there was a recent paper as well on, called DNGO. That's the abbreviation, but so essentially they have like a procedure which is similar, except that they don't do like multitask learning. There's a single task, and they have like a two-step procedure. So first they're going to optimize like the linear regression model and the neural network, then fix the last layer, and then plug a Bayesian linear regression model and learn then that one to do like Bayesian optimization. So it's just two-step procedure. So in this case, we don't have to do that. We just learn, at the same time, we learn the Bayesian linear regression model and the neural network. And if you want to know about the details of implementation, you can look at, maybe discussed with Matthias yesterday, or you can look at the paper on how to do that and how we can apply autograd in this type of problems. So now how are we going to apply that to hyperparameter optimization? Well, how do we do ground starting, the procedure of hyperparameter optimization? So what we're going to do is that we're going to consider when we have this type of architecture, we're going to do like a leave one task out procedure. So essentially, we're going to collect, if we would like to optimize, well, not the second task, we're going to collect few data points in the other tasks and then start without any observations in this target task and see if we can do better than without doing the warm starting aspect, without using essentially the shared representation. So the first, I still have a couple of minutes here. So the first example is like to illustrate how it works is like a simple toy example where we have quadratic functions here that we'd like to minimize. So every task is, so at the bottom here you see like the form of the quadratic function. So every task has a different set of alphas, so A's parameters. So we have like 3 parameters here and they're like randomly drawn from some multiplied Gaussian distribution. And so we have a bunch of those related tasks, and we would like to see whether, if we have seen and optimized a couple of those functions before, can we leverage the representation that we learned, and can we speed up the optimization of a new task and for a new set of A's. And so what we see here on the left, we compare to doing random search for hyperparameter optimization. We look at essentially the ABLR model without transfer, so that's ABLR neural networks. When you learn the representation for every task, there's ABLR RKS, which is random kitchen sinks. And then we have the GP as a reference. So the first thing to see is that, well, the ABLR models are able to do a pretty good job. When you learn the representation, you're able to, so you have like, if you look at the 3 ABLR models without transfer, those are the plain lines, the red ones, the black ones, and the black one and the blue one. So they're doing much better than random search. And you have a GP is doing slightly better than, for example, ABLR, which is not surprising given, I think, the GP models are very powerful and have very good estimates of the uncertainty. So that's quite intuitive. But what we see is that if we do it in the transfer, so once we do it through the transfer learning across multiple tasks, we really have like a speed up of finding a good solution way faster. So in this setting, essentially we see that transfer has a benefit over non-transfer, and you have like a similar behavior between GP and ABLR with neural networks. If you look at the right plot, well, this is compared to other neural networks-based approaches, and we have like essentially DNGO is the one that just described before, and Bohemian is is using a Bayesian neural network for hyperparameter optimization. And so basically, we have like we've extended both of those methods to include the transfer learning aspect, and we see that in fact, we are doing a better job with this simple Bayesian linear regression models. And so the reason, the intuitive you can think of, the reason we're doing a better job is that it's probably a simpler model to learn. There's less complexity, and so we're able to fit the parameters or estimate the parameters better in this setup. So after this story example, where we looked at some real examples, so we looked at a whole bunch of data sets in OpenML, and we retained the ones that were the most interesting, so the most interesting methods. So we have on the left data sets that were trained with SVMs, and on the right XGBoost. And the take-home message is that whenever you do the ABLR models with transfer, where you learn the representation, you're able to do a much better job at optimizing your hyperparameter optimization job or your model. If you look at the ones that do not do transfer, well, they're roughly in the same league as random search, but whenever you have the transfer, you're able to do a much better job. At least in the SVM case. In the XGBoost case, well, you get some benefit as well, but the uncertainty is much larger, so thereby it's much larger. So one thing I forgot to mention is that the model here that we had, you might have seen like CTX, so that's context. So if you think about the previous model that well, the previous description of the model. So what you could also do is that if you have side information about your task, you can easily append it to your hyperparameter configurations. And so if you have information like some information about your task, this is like some context information, you can use that. In the experience that we used, it didn't really help. The representation that we were learning was actually like taking care of that implicitly. But this is at least an option that you can investigate in some other settings. And so if you think about the model, where you can look at different tasks, different hyperparameter optimization tasks, but you can also look at a different setup where we can potentially use different types of signals, like auxiliary signals. And so here the setup is like now the Bayesian regression models are not previous hyperparameter optimization jobs, but there are other functions that are correlated with your target function. So again, we can think about the target function being the validation loss, and another auxiliary signal could be a training cost, could be like the training loss, or some other variant of those quantities. And so the question is whether using these additional signals is going to speed up like the quality of your hyperparameter optimization task. Essentially, are you going to be able to learn a better representation quicker? And the answer is yes. So here you have like the essentially the different curves where you, as before, if you look at ABLR, where we have ABLR plane, you have ABLR, so just using the training loss in addition to the validation loss. So 2 means like there are 2 tasks or 2 signals used to learn the representation and do the hyperparameter optimization task. Then we can add the cost, that's 3 on the bottom, and at the very bottom we have like the cost plus an epoch-wise training loss. So every time we have we do one epoch over the data, we use that as well as an additional signal. So in that case, we have like 21 tasks in parallel. And what we see is that using those signals is really helping a lot, finding a better representation and speeding up hyperparameter optimization. I think I'm running out of time, so time for the conclusion then. So essentially, this talk is about like automating ML, like I talked about like Bayesian optimization. So one of the general setups is, messages here is I think that Bayesian optimization is quite interesting approach for like automating ML. Like it's not only algorithm tuning, but it can also be used for model tuning as well as pipeline tuning. The things that I really like about Bayesian optimization over other approaches, that it's model-based. And that's quite powerful because you can incorporate additional information you have about your problems. For example, we had some work on including dependency structures. So if you know your hyperparameters have some dependencies, that helps, of course, like exploring your hyperparameter space. But since you have this model-based approach, you can also start using auxiliary information, for example, to do warm starting hyperparameter, doing transfer learning at a hyperparameter optimization level. I think it's really a key building block in meta-learning. And I hope I was able to convince you that you can do some useful representation of for hyperparameter transfer learning. I think it would be nice to continue and see what are some extensions of that, of things that we can do more effectively in the future. That's it. Questions?
Thanks a lot. Any questions from the audience? It's coffee time, but I don't want to keep you away from coffee. But I think some questions will be.
Hi, thank you for the nice talk. So, which kernel function did you use for the GP?
We use a standard like material kernel that's used. So, yeah.
Okay, because I mean, I'm just curious that I think it's a very good application, and I think that I would like to see like the comparison with using a GP with the covariance function, that like the neural network covariance function. That there's like these 2 papers in ABLR this year that show like if you have that many layers and like an infinity wide neural network is the same. Well, it's equivalent to using a Gaussian process, but that's kind of a limit argument. So I think that it would be interesting to see if the representation that we learn with the GP with this covariance function is like in a way more like well, how does it work in this task? Because it's not clear for like Bayesian optimization, because the GP is like kind of informing the decision rather than you're not using it straight like that.
Yeah, I agree. So one thing is definitely like if you look at the GPs, what people do, they have like a default choice of the kernel, which is suboptimal, right? That's for sure. So this is a way of learning the kernel. But so what we did here is really trying to look at a very pragmatic and like scalable approach. You can be more like sophisticated, and so the question is if you're more sophisticated, what do you gain out of that? And so far, so the test that we've done is that it's not so easy to get better results, and I think one of the reasons is that you're able to fit like the parameters. Since you have this linear model for every new task, you're very effective at fitting them very quickly. But definitely there's some room for like you can look at multitask GPs and learn like having other approaches, most of just to learn the decent kernel for this.
But I think that it would be an argument in favor of your approach.
Yeah.
Because like if yours is like less costly, so it makes sense. Thank you.
So I have two quick questions. One is on the relative trade-off between if your function evaluation is very efficient, right, or if function evaluation is very costly, then you can spend more time on the modeling versus less time on the modeling, right? Because if the function evaluation is so cheap, then basically there's no point for modeling. The random search is actually very effective, right? So how do you balance that trade-off? The second question is, have you done comparison with the baseline where the kernel is learned, like during Bayesian optimization, and the kernel is sort of transferred for the new task?
So to the first point, which is more like a Bayesian optimization question, I would say that this is for the cases where it's, so if your evaluation is cheap, I don't think you should be using probably Bayesian optimization or Gaussian processes. You want to probably use something which is like something like Hyperparameter or like banded values, where you can evaluate maybe its configuration multiple times. And then the question in the middle, then it's a bit of a trade-off. So I think this is, well, you're in between. So I think I would rather think those are hybrids between those models. It's not like a clear winner or what you will use in which cases. Of course, you can easily also combine both approaches. So I think there was a recent paper in some experiments that work internally. So you can do like first like start with a banded type of approach and then try to refine. So there's kind of a being in the middle, but I don't think there's like an easy way of deciding which one. Well, at least I don't have a good answer to that. Probably depends a bit on the type of problems you're looking at and what is really costly. What's the cost of what's the type of cost as well that you're looking at. But yeah, so you have the two extremes in the middle. It's not quite clear which one you would use. On your second point, so when you're saying like you're suggesting like learn a kernel and then just like transfer use the kernel in this new application. So I think this is the new for example task. So to some extent this is what we're doing here, right? We have this shared neural network which is learning a kernel. It could be more explicit in that, and we haven't done that comparison.
So a few more questions. I think we can take this to the coffee break after that.
So just a quick question. So when you were using random feature extensions, I was curious how many basis functions you were using. The other question was related to computational complexity. So you mentioned that GPs are too big in the number of training points, but for Bayesian optimization, the testing time complexity is also quite critical, especially if you're going beyond, say, text improvements like knowledge gradient. So I was curious, like, how many times are you actually querying the function you're trying to optimize typically, and how many basis functions are you using in your random feature extensions?
So the random, so we did it. So that's, I didn't have the time to talk about it, but we did some comparisons and we tried to. So we did for the. So we first we looked at the same number of essentially same dimension number of features, which is unfair because essentially you have one scaling parameter. I think so. What we did is we looked at a dimension up to the point that the computational complexity was the same as when you do the training. So essentially during your every step of your business optimization that was of the same way. So we had like a much a larger dimension, and even if when we increased the dimension of the RKS features, we were never able to meet the same performance of learned the relative representation. And the second question was about like the time complexity.
The testing time complexity. Like, it seems like that could be quite critical. And I was just curious, like, I mean, training versus test. So I guess.
Well, so we're training on the fly. So every new data we have to do updates. So it's really our critical. The thing that we're looking at is how do you update your surrogate model. That was the really the part that was of interest, the critical part that was of interest. And
did you query the function you were optimizing?
For every, so it's like there was iteration. That's one by one. In all the experiments, it's like sequentially one by one. So it's not. We don't do like we don't fantasize and we don't do multiple queries. Oh, you mean for evaluating candidates? You mean?
How many iterations?
Can I recommend taking minutes of time for just going into detail there? Dasha had one more question, and I think we can thank the speaker again on chat. Sorry.
I really enjoyed your talk. I have a question which is maybe a question for all the competing techniques too, but often when I use hyperparameter optimization to train neural networks, there's a regime in the hyperparameter space where it diverges or the hyperparameters are not feasible. And often the best performing hyperparameters are like right at the edge of that regime. And so I often find that like random search works better than tuners, not because the tuners are doing worse on the function, but because the tuners are very bad at handling slight diverging reaching in the hyperparameter space. So I guess how do you handle that?
So, well, I mean, for me, those are the types of prompts where you, well, not the types of prompts, you would like typically to learn the constraints or those aspects that you describe. So sometimes it's deterministic, typically this is not, you don't know that in advance. So I think, so one of the things that we looked at is like, how do you learn that? That's a side function that you learn at the same time. So you know what you over time, if you have like this transfer learning, you can, that helps a lot as well. And it fits very well in this setup because tasks is a very loose definition. It can be jobs, can be signals, it can be both of them essentially. It can be constraints as well. Yeah. So that's also why I think the transfer learning is interesting because you can learn that over time.
Let's thank the speaker.